Let's talk about this idea about cis and trans and define the idea of what this is, and then talk about stabilities of different molecules. So because the pi bond is going to be rigid, it can't rotate. And so once you put groups on that pi bond, they can't interconvert. It's not like a single bond which can rotate freely. So what we've got this idea of cis and trans now, this idea that we've got over here, we have, if we define a line that goes through the middle of this alkene like this, and we can recognize that the two carbon groups are on the same side of that line, that makes it the cis isomer. Over here, if you have a hydrogen there and a hydrogen down here, the two carbon groups are on the opposite side of that line, and therefore this is the trans isomer. Now that's straightforward enough, but because science developed all over the world, we have different ways of saying the same thing. We'll have to deal with E and Z in a second, which are the same as cis and trans. We need to be aware of a few things. There are limitations in chemistry. If you tried building some models and you built the model kit and you built sort of small molecules with very small rings, they're often very strained and your molecule looks like it wants to break open. Okay, that's important. Alkenes are very similar to that. You'll find that for the small molecule, the small cycles, you can only get the cis isomer. So we typically don't label cis or trans for this type of compound because it's impossible to have the other one. We can look at that, for example, with cyclohexene. That is the cis isomer because the two carbons here are on the same side of that double bond, but you cannot make the trans isomer. It's impossible, it doesn't exist. And the reason is if you try to do that, you'll end up with something like this, something rather odd like that, with not enough atoms to make a stable molecule. You'll end up with a thing that's trying to sort of wrap around on itself, and it just doesn't work. So, for example, this one, cycloheptene, cyclohexene, cyclooctene, they only exist as the trans isomers. As you get bigger, and you start putting more carbons in here, you can make the trans isomer. In this case, I think we have, what, 1, 2, 3, 4, 5, 6, 7, 8, 9. That is going to be maybe observable. You can make it in the lab and you can see it, but maybe it doesn't exist very long. Maybe it's too reactive and you have to look at this at low temperature. It's only when you get to C12 that you start to get the trans isomer being equally stable, right? And the answer is simple. You have enough carbons to be able to tie this thing in that configuration so that the trans isomer is now stable. Okay, below that, it doesn't work. So be careful there. When you're looking at answers on answer keys, where is the cis, where is the trans for a simple cycle like that? It's because the other one doesn't exist. We don't bother with doing that. Now, if you know R and S, you can do this. There's nothing different here. You can think about the Carnegie-Prelog rules and think about how you designate R versus S, and we can use the same rules to do this. Now, because this language sort of developed across the world, we've got different ways of saying the same thing. So anybody know what E stands for? Anybody reading ahead? It's a German word for opposite. It's entgegen, okay? Entgegen, opposite from, or across from. And that's obviously developed in the German pharmaceutical industry. And that then is another way of saying trans. So trans is E and cis is Z. I always remember them, cis and Z sound the same. The other example, Z here, is the German word for together, zusammen. And if you think about that, that makes sense because if the two groups are on the same side as each other, that's what they're doing, Z. So what you need to pick up very quickly is how to name these things and how to use this label to differentiate between one and the other. And in some examples you see cis and trans, and some examples you see E and Z. And if you're going into pharmacy or medicine, you'll see both, so you need to be conversant with both of them. Over here, we have to develop a little system to be able to say which is the cis and which is the trans or the E and the Z. So what we do is we isolate on each carbon and ask what is attached to it directly, and then set a priority scheme like we did for the R and S. So if I'm dealing with this carbon in the circle, which is higher priority, F or C? F, right? We're using the same atomic number criterion that we did for the R and the S. On the other carbon now, which is higher priority, H or N? N. So is that the cis or the trans? That's the cis, and we could also call it the Z, right? So that's cis or Z isomer of that compound. If you want to make the other isomer, you have to physically take off two of those pieces and swap them, just like we did for the R and the S to be able to change those. So on the other example, on the other side, you can see here the N has been taken over there and the H has been swapped. Now the N is the higher priority, the F is the higher priority. They are on the opposite side of this imaginary line through the alkene, and that then is going to be the E isomer, or in other words, the trans. It's fairly simple. It's just an extension of the Carnegie-Prelog rules like we saw before. There's nothing too tricky about this one. There you do it, okay? Same rules. Just do it simply, keep it simple. Don't make up your own rules. Save that for graduate school. Just follow the rules. Everybody okay? It's Wednesday. My dog says hi. As I was leaving this morning, it's like, see ya. Bye. Say hi for me. Just did it. Okay. We are talking about the same rules of priority, okay? That's already been covered. And we need to make sure that we're comfortable with how to use this, so let's do some examples. Again, just take your time. There's nothing complicated here. Just follow the same rules and away we go. So I've got a carbon here on the alkene and a carbon here, and on the left-hand side I have carbon and carbon. So what do I need to do? Go further out. Follow this further out. And take your time. What's attached on this carbon down here? CCC. What's attached on this one up here? OHH. Now, which is higher priority, OHH or CCC? OHH, because the O beats the C. So this one is higher priority up there. On this example, you have to go further. There's a CH2, there's a CH2. I must go further out. Here I have, what's attached to that? CHH, what's attached to this? CCH. So we've learned that rule, it's in there now, that's good. And we can see now that this is higher priority on that carbon. So what is that, cis or trans? Trans, E or Z? E. That's all there is to it. Okay? Quick examples, look at that. Can you tell me what it is straight off? Cis or trans? Trans, okay, Br beats F, Cl beats C, they're on the opposite side, that should be the trans isomer. This one here, any ideas? Cis, F beats C, and C with oxygens attached beats C with hydrogens attached, so they're on the same side, that should be the Z isomer. Down at the bottom, more complicated because we don't have any heteroatoms, it's all carbon, so you must take your time. Which is higher priority on this carbon? This stuff or this stuff? The bottom on the left. What about over here? The C triple bond N, because you get to nitrogen, down below you get to hydrogen. So they're on the same side or the opposite side? Opposite, therefore, E or trans. Now this one is in a cycle. You've got to be careful now because E and Z, you've got to worry about the priority schemes. Is it cis or trans? Trans, right? The Br beats the C and the C beats the H. Br over here beats the carbon attached, and over here C beats the H, and that's it. Very straightforward points. Well, we have to worry not so much for Friday, but certainly after we come back on Monday, this idea of stability in alkenes, because it governs what happens, it governs what products you get. And next week we'll head into this rather confusing idea of major products, and major products, and minor products, and major products. And it's very confusing. But we'll save that for next week for the people who come back. It turns out, for a very simple reason, transalkenes are often more stable than the cis. And these pictures are trying to show you why. The transalkene, the two large groups, are far away from each other. They're pointing in opposite directions. Over here, in the cis isomer, the two large groups are getting close to each other. And again, you've got to keep in mind that whenever we draw these pictures out as sort of stick figures, they're not that accurate. So these methyl groups don't look like they're that close to each other, but when you build a model of it, yes, they are. They're getting quite close to each other, and that's a problem. So it turns out this is a little bit less stable than this, and that will be very useful in the near future. Steric environment now means a big deal. We can measure this, you can quantify it by doing experiments, and you can take, for example, the two butenes. This is cis-2-butene, and this is trans-2-butene. And what we're trying to do here is come up with some method to show their relative stabilities. And this is very simple. You're just combusting them. You're burning them in oxygen. And the idea is that if you start out with this molecule and this molecule, you get the same products, and you get the same number of moles of products. So you can quantify this relative to each other. You can do this quite easily, and you'll find that this one is more stable than this one, and there's some proof, right? There's some evidence. If you do physical chemistry, which the engineers can't avoid, you're going to have to do some of it, you'll talk about this stuff in the future, right? Very straightforward stuff. So yes, the cis is usually more stable than trans. On top of that, you've got to worry about classification of the alkene. How many groups does it have attached, and what will the effect of that be on the stability of the molecule? So at the top left, I think we did this the other day, that's monosubstituted, yes? Everything else is hydrogen, you have one carbon attached. You have disubstitution here. You'll see multiple patterns of these things. You can put the groups together different ways and get the same sort of idea. We got the trisubstituted, and we got the tetrasubstituted. Well, the fact is that these things over here are more stable than these things over here. And the argument goes back to something we've already done. It goes back to the idea of sort of inductive effects and alkyl groups pushing electrons towards things, helping stabilize. And it also deals now with a different hybridization pattern on the alkene. We have sp2 carbon, and sp2 carbon is more electron greedy than sp3 carbon. You want to quantify that? You want to go back and see something you've already done with that? Go look at the acidities of an alkyl group versus an alkene versus an alkyne. What was the pK of this guy when he had a triple bond? What was the pK of that approximately? 25. What was the pK if it was just CH3? 50. That's 10 to the 25 difference. That's a massive difference. And it was all down to the fact that this was sp hybridized, yeah? And sp hybridized is a bit more electronegative, it holds the charge better, and so it's a more stable species, which makes the acid a bit more acidic. Well, we can say the same thing down here. What's the hybridization right there? sp2. So sp2 has 1/3 s character, 2/3 p character, right? And so it wants more electrons more than an sp3 carbon. It's got more s there and it's pulling electrons towards itself. So what do we push electrons with? Think about carbocations. What was the benefit of having alkyl groups next to a carbocation? Was it good or bad? Good. Haldeman, you ready? What stabilizes a carbocation? Hyperconjugation, Haldeman. And what is hyperconjugation, Mr. Haldeman? From adjacent single bonds. Well done, well played, 1-0 you. Those alkyl groups benefited something that wanted electron density. The more of them, the better. That's the basis of hyperconjugation. Now, this isn't particularly hyperconjugation, but it's close. If these carbons in the sp2 hybrid alkene, if they want electron density, then alkyl groups can give them electron density in the same sort of sense as hyperconjugation. So the more of those alkyl groups attached, the better. In this case, we have the tetrasubstituted system. There are 4 of those alkyl groups. They might be methyl groups or ethyl groups, whatever, but they have those adjacent bonds. They can push electrons towards the sp2 carbons. So it really is the same argument. Okay? sp2 carbons want more electron density than sp3. The alkyl groups can give that electron density up. So we stabilize this thing by having more alkyl groups attached. And in general, maybe not so much for Friday, but certainly for next week, the more highly substituted product will prevail. Joseph. It will be in the next chapter on. This is isolated as its own molecule. There's nothing else around. You put something else in its presence, a positive thing, an electrophile, it will go after it, right? And then we'll talk about the relative nucleophilicity of alkenes, but that's next chapter. That's chapter 9. That's a huge chapter. It's like 1,000 slides. So the idea now is that the more substituted you've got, the better the better the stability is. But first off, you have to recognize what patterns they are. Are they monosubstituted, di, tri, or whatever? So look at these systems. Top left. What's the substitution pattern on that molecule? Is it tetra, tri, or di? Tetra. So the question is, okay, how many carbons directly attached to the alkene? And the answer is here, I have 4. So that example there is a tetra-substituted alkene. In the middle, how many attached? 3. So what is it? Tri-substituted, okay? Won't be quite as good as the one on the left. This one here, how many attached? 2, di-substituted, right? When we get to the isomeric ideas next week and we have to decide which one is favored, often it will be the most substituted. So we have to very quickly be able to say this is better than this, which is better than this, because of the substitution pattern, because of the ability to donate electrons to the alkene carbons. Not easy to get your head around that one. Looking at these things here, what about on the left? What is the left system? Mono, di, or tri? Mono. If you're not happy with that, put the hydrogens back in. And in this case, you're going to have 3 hydrogens. And since you need 4 things attached to the alkene, there's only 1 carbon left. All right? That's mono-substituted. What about the middle one? Di-substituted. What about over here? Tri-substituted. Very simple to pick up. Very easy to get wrong. Yeah? Check it. Make sure you're happy with it. Down at the bottom left. What are we looking at? Di, tri, or tetra? Di-substituted. What about here? Tri-substituted. What about there? Tetra. Which will be the most stable of all those 3 molecules? Tri. Okay? And you'll find next week it gets very complicated because systems will go off in their own little paths, and system will break up. Some molecules go over here, some molecules go over here, and you can get 2, 3, 4, 5 different products in the same system. Not just yet, but next week. Okay. I have one reaction to talk about today, and it's an elimination process in which we take out some pieces from a starting material and we produce an alkene. It's a very, very useful way of making alkenes, which then can be used for other things. So what we're doing here, very subtly but carefully, is we're starting to build up a collection of reactions that we can use. This gets to be more fun after this test because we start to put it all together, and we start to do stepwise synthesis, where we take molecule A, react it with a reagent, and turn it into B. Right? Having said that, let me take a time out for a second. On homeworks and on practice exams, you're starting to see these sequences. You're starting to see a starter material, and then 4 reagents listed on top of each other, 1, 2, 3, 4. You've got to be careful there. Some people are thinking that I take my starter material, I react it with number 1, I get something. Then I take my starter material again and react it with number 2 and get something else. No, it's a sequence. You take molecule A as your starter material, react it with the first reagent, you make B. B then becomes the starter material for the next step. Okay? Does that make sense? If it doesn't, you need to ask. So make sure you're seeing that. And we're building up, by next semester, we'll be doing 10, 12, 13 different steps in that type of sequence. And it can be kind of fun. On my practice stuff for next semester, there's a 37-step synthesis in which we go 1, 2, 3, 4, 5, 6 all the way through. And by the time you get there, if you're still here, it's fun. And you feel accomplished because you're like, wow, this isn't so bad. You've actually put something together. Now let's talk about the E2. We need to prove that this is going to be bimolecular. We need to come up with some conditions, and we need to keep it separate from the stuff we've already done, because they will interfere, they will interact, and this can be a big problem. I've done my best to keep this separate for Friday. Friday's a fairly straightforward, coherent test. Monday, when we all come back, it gets messy. So what we have now is an elimination reaction defined by taking out two pieces from a molecule. We are taking out two pieces from this molecule, and we are making a double bond. I'll use some terminology that will become more apparent later on. This molecule is said to be saturated. All of its valences are single bonds. It is saturated, there are no double bonds. The molecule on the right is said to be unsaturated when we have put in a double bond. We'll talk about stabilities next week, we'll talk about how we get there practically in the lab. But right now, we're trying to rip things out. We're trying to take out a leaving group. Now, what do you think a leaving group will break off as? Will it break off as a positive thing or a negative thing? A negative thing, right? They're not going to change like that. It's going to be negative things. So if I'm trying to take out electrons from here, and I'm trying to make a pi bond, I need a pair of electrons. If that leaving group is taking off with a pair of electrons, I need an extra pair of electrons to make the pi bond. Any ideas where they come from? They come from hydrogen. They come from the CH bond right there. You've got to be careful here. You can get this confused very quickly with migrations. It's not a migration. In a migration, it's H hydride. It's H minus technically that's moving across. It's taking its electrons with it. In this case, the hydrogen will give up its electrons. Where have we seen that before? Something comes in, picks off an H, and something breaks off. What's that called? Acid-base reaction. That's all it is, right? It's an acid-base reaction. So this elimination process will involve leaving groups breaking off and acid-base chemistry, putting it together in a different way to get a different outcome, a different mechanism. So one possibility for this, in terms of this happening, is concerted, and the other one is stepwise. So if you've become conversant with these ideas of nucleophilic attack and loss of leaving group and proton transfer and rearrangement, this shouldn't be so bad. And I'll tell you right now, in this elimination stuff that you'll do by Friday, no rearrangements. Okay? No rearrangements so far. Next week, oh boy. Rearrangements left, right, and center. So we've got to be careful here. We're going to decide that, okay, leaving group breaks off. I'm going to use this arrow, presumably, the leaving group being lost. And I'm taking off a proton. So I'm going to do a proton transfer. That's the combination we will use for this particular mechanism that we'll call the E2. So look at that at the top. Something has to break off as a leaving group, and a proton has to come off as well. So now we have to discuss the timing of the events. When do things happen? And to summarize that, thinking about chapter 7, what's the essential difference between an SN2 and an SN1? It's when things happen. In the SN2, everything happens at once. It's concerted. In the SN1, what happens first? Loss of a leaving group, and then nucleophile comes in. Overall, the same transformation is happening, yes? You're substituting, but they're happening in different sequences. That's all that's going to happen in this chapter, is two different sequences for how elimination can happen. So let's think about this. In analogy with the SN2, where everything happened at once, how about this? An elimination process where everything else happens at once. So it's concerted. And the conjecture here is that the base can come in, it can grab a hydrogen, and it can kick out a leaving group. In the meantime, that pair of electrons right there are going to form your pi bond. So keeping a track of what happened there, a lone pair from the base is used to bond to the proton. That gives us the conjugate acid. The pi bond comes from this pair of electrons that the proton is giving up. We're putting that pair of electrons between two carbons so that all the octet rules are happy, everything's satisfied, and that gives me the alkene. And over here is my leaving group. Now, why on earth would you want to do this? Why does this work? Well, let's say this is O minus. Okay, let's say this is some oxygen base. And let's say this is Br minus, that broke off. Which is more stable, Br minus or O minus? Br minus, by how much? A lot. So the driving force of this reaction is to get the negative charge from O minus and put it onto the Br minus. That's all that's happening. So now we have to worry about the timing of events. There's one possibility that we can call a concerted pathway. How many molecules involved in that step? 2. So do you see where bimolecular will come from? Like it did for the SN2? It'll be bimolecular because both of them have to be present for this to work. What's the opposite possibility? Stepwise. So what do you think can happen in the stepwise process? The leaving group breaks off, and then what happens? Then you get an acid-base reaction. That's exactly analogous to the SN1, SN2. We won't get to the E1 before the exam, but for the SN2 we will. There's the other pathway, okay, stepwise, in which the leaving group breaks off for similar reasons it broke off in the SN1, and then the base comes in and it takes off the proton next door and you get the alkene. So they're parallel. SN2 with the E2 and SN1 with the E1. Those are the possibilities. By Friday, by the end of today, I will be here. This will be next week. Joseph. We'll get there next week. We don't want to confuse things too much for Friday because I've got a sense that things are already pretty confused. Yeah, it's the degree of confusion that we're dealing with here. Right, let's get on with this. This is going to be provable by experiment. You can start to put in you can put in extra base and things will speed up. You can put in extra substrate and things will speed up. So that means that both of these things are present in that rate determining step, and both of these things are necessary to go to product if this is an elimination that's bimolecular. Therefore, we'll call it the E2. Elimination bimolecular to give an alkene. Well, in terms of substrates and what does this, you've got to be careful because we're starting to mix things up now. We had some fairly straightforward ideas for this is SN2, this is SN1. That usually is not a problem for people. When we throw the E2 in, it starts to become a problem. So there's your mechanism. That is the E2 mechanism. It is analogous to the SN2. And Joe, you're thinking ahead, but that's good. This here is a base. What can a base also be by definition? A nucleophile. And a nucleophile can be a base by definition. So didn't we just spend a week or so talking about things with electrons going after this carbon? Yes, we did. And we developed the SN2 and the SN1. Now look at that system, the way it's been drawn out. If this base is also capable of being a nucleophile, why can't it go for that carbon? It's tertiary, it's too crowded, that's it. You start to think like chemists, right? Just putting the rules into play. That carbon is too crowded. Now look at the base. If the base is hydroxide or methoxide or something that's really powerful, it is not going to wait around for other things to happen. That's the reason the SN2 is such a good reaction. It just goes in and that's it, it's done. The SN1, you wait for things to happen because you don't have a powerful nucleophile. Now we have something that, you know, if it could be a nucleophile, it would be a nucleophile. But the substrate here precludes that because it's tertiary. The nucleophile just can't get to where it wants to go. So it changes roles and it becomes a base. Because overall, you want this unstable thing to become this stable thing. That's all that's happening. That's the driving force for this. That's why it's happening, the motivation for it. So let's look at the possibilities here. Overall, we'll call it the E2. If you add more base, it gets faster. You add more substrate, it gets faster. It's elimination because we're getting an alkene. It's not substitution anymore. And in terms of the arrows being used, that is a proton transfer. Now, I've had questions in my office hours this week, good questions about what's the difference between a carbocation rearrangement and an acid-base problem. Well, an acid-base problem is dealing with H+. The H gives up its electron pair. In a migration step using H, the H stays with its electron pair. The electron pair is important because it goes with the hydrogen to bond to the next atom and give you a better carbocation. So that is not H+ moving across, it's H with its electron pair. This is the opposite. This is the H giving up that electron pair in this arrow here to form that pi bond. That's the big difference. You've got to be comfortable with that so you don't get them mixed up. The other step here, happening at the same time, is loss of a leaving group, and that's where the alkene comes from. Again, the question will be, why does this happen? How is it possible for this to happen? Really two reasons. It can't do an SN2, right? Really good nucleophile wants to do SN2, can't do it here. The other answer is you want to put the charge on something better, and something better is typically Cl-, I-, Br-, or one of the sulfonate leaving groups. Anybody want to say anything? It's very quiet today. Are we getting nervous yet? No. Right. Let's see. Okay. Examples. We have to be comfortable with what's happening, and we have to be very careful. In this system, looking at that starter material, from what you've learned before today, I hope, because the homework's due tonight, is that this system might do an SN2 because you're looking at that NaOCH3 and you've hopefully learned that that's a good nucleophile. And you're correct, that is a good nucleophile. But in this system, that isn't going to happen, right? So the question might be, as you're starting to think about how to solve these problems, is this an SN2? Well, if I throw in a solvent, what's a good solvent for SN2? DMF. Let's put DMF down there. I could even set this up the same way. We might run the same reaction in the lab. Okay? NaOCH3 and DMF. If that's what you're memorizing and that's sort of your clue as to do an SN2, you won't get the right answer here because you haven't solved the whole issue. What is the problem here? Why not do an SN2? It's tertiary. You've got to see the bigger picture. It is tertiary. It can't do an SN2. But that O- wants to react quickly. It's not going to wait for other things to happen. It's not going to wait for a carbocation to form because it's too reactive, it's too unstable, and it wants to become something stable. So then you have to worry about where things will happen. Okay? We're going to start using this term regiochemistry. And regiochemistry is nothing more complicated than, the word region, where are you from, what region are you from? In this case, regiochemistry will be where does the double bond go? And that's an important word for certainly next week and beyond. Regiochemistry. Now, in some instances, you can only get one product. In other instances, you can get multiple products. You can get 3, 4, 5, 6 different products. In this example, there's only one possible. What I'm looking for here is a leaving group. Check, got that. And I'm looking for a proton next door. And that proton has to be on the beta carbon. Don't forget the one with the leaving group attached is the alpha carbon. The one next to it is the beta carbon. And that beta carbon must have a proton or else you can't eliminate there. So I have a CH3 right there and I have a CH3 right here. And how are those two CH3 groups related? Are they the same or different? They are the same. So does it matter which one I attack? Does it matter which one I take a proton from? No, it does not. So if we do the elimination reaction where the negative oxygen goes after that proton and this then breaks off, that is the E2 process. And it is analogous to the SN2. It's bimolecular, add more base, it goes faster. The problem now is you've got this extra bit of information that could screw things up. You probably just got happy, hopefully you got happy, with what is SN1, what is SN2. Now we're making it more realistic by putting the other alternative in. So we only get one product. Why not take any protons over here? We've got all kinds of protons over here. Why not take them from there? They're too far away. They're not beta. They're too far away to participate. So that's no good. Why can't I get a carbocation here? Why doesn't it just, because it's tertiary, why doesn't it just say, hey, I'm just going to blow apart? Why not do that? Because the base is so reactive, it won't allow for that to happen. So you've got a lot of information there to decide what's going to happen. What's going to be is it going to be substitution? Is it going to be elimination? Now the fairly obvious ones, and for Friday it's fairly obvious because we haven't really got into this that detailed yet. These sorts of ideas now are starting to become complicated. You'll get to know this guy a lot. Okay, this material here is very useful for elimination reactions. And this slide is worth spending a few minutes on because it does sort of bring a lot of things together. I'm going to make it more complicated again by adding one of our polar aprotics, not to confuse you, but to make it more realistic about how you would do this in the lab. And this material KO is something that you will grow to appreciate. Potassium is positive, oxygen is negative. Simple enough. Which is the basic part? The oxygen. So if you did the pK of the conjugate acid, what would it be approximately? 16. This one's about 18 for reasons we talked about in the past, but it's going to be in that region. Does that make this a strong base or a weak base? It's a strong base. Jenna. Yeah, here and here. They're both the same. It does not matter because they're both the same. You get the same product regardless where you attack right there. Okay? So this is now thinking about the subtleties. Why are we changing the mechanism all of a sudden? Well, we have to. Because this one won't do an SN2. And look at your checklist. We did this on Monday. You got a checklist to decide what's SN1, what's SN2. What type of substrate is this? Primary, secondary, or tertiary? Secondary. What can it do? SN1, SN2, or both? It could do both, and that's the problem. In this example, it's not doing any SN2. You've identified this, and we've said it's a reactive molecule. It's not going to sit around and wait. It's going to go after the substrate. Any ideas why this isn't very good at SN2? Pro logo? Big, large. Okay? So we start using this sort of language now about That is large. And if it's large, it's not going to get places easily. It's not going to be able to attack as a nucleophile very easily. And if you put it in the presence of a secondary carbon, it's going to have a tough time getting there because that secondary carbon is branched and it's going to block. Put it in the presence of a primary carbon, you think you might get some substitution? Yeah, right? We'll deal with that later. But in this case, we choose often this material because it is so big. And it's a lousy nucleophile because it is so big. You think about what made a good SN2, it was accessible substrates. What made a bad SN2 was crowding. Well, this is crowding in the nucleophile now, not the electrophile. But they both add up and they're both bad. So in this example, we've got to choose a proton to take off because we know we can't do a substitution. Let's do a checklist. It's secondary, yes, it could do SN1, SN2, or what we're now calling E2. It could do any of them. It is in a polar protic solvent. That might trigger the idea of, okay, this is going to be an SN2, but it doesn't do an SN2. The problem being that the base is so big, it cannot get to the substrate. So now we switch roles. Instead of this thing being a nucleophile, it's changing into a base. And that base needs a proton to go after. And if we look at this, Jenna, what's the relationship between those protons? The same or different? They are the same. So it doesn't matter which one you attack. You're going to get the same outcome. So my negative oxygen here, identified as the base, comes in, grabs that proton. Can I stop there? Why not? Well, why? Think fundamentally. Why can you not stop there? Why can you not just stick that oxygen to that hydrogen? Breaks the octet rule, right? Too many electrons. Too many electrons. So where am I trying to push the electrons? Do I want to push my electrons towards carbon? Is carbon good at taking a negative charge? No. Where do you want to push them towards? A good leaving group. So that's why this happens. This bond now is breaking, pushing those electrons towards that carbon to make a pi bond, and that allows for the iodide to break off as I-. There's no other mechanism there, but no other possibility that gives you a good stable outcome. The alkene is fine, the iodide is very good. E2, if I add more of this base, what happens? Faster or slower? Faster. That's all there is to it. So the last one here, and then I'm going to draw a reaction profile because I want to prove that before we take the exam. Look at the bottom. This is really the last thing I want to teach before the exam. But it's foreshadowing what comes next week, this idea of different pathways for the same system. And you happen to be on top of this stuff so much that you can tell me what's going to happen when. I have NaOCH3, and I might put it in some nice polar aprotic solvent like THF. We've seen THF before. It's this guy, which was an ether from the past, and it's nice, it's cheap, it's easy to work with, polar aprotic. And those clues might ask you or might tell you to do an SN2. What's the problem? Why will this never do an SN2? It's tertiary. Yes, I think people are starting to get this. It's good. It's tertiary. So it can't do an SN2. But tell me about this base. Reactive or unreactive? Reactive. Yes, it's reactive. What does it remind you of? It reminds you of hydroxide. You know hydroxide is reactive because if you put your hand in it, it hurts. You always go back to that same old idea. So if it can't do an SN2, it'll do an E2 instead. Instead of this behaving as a nucleophile, it'll behave as a base. Now you've got to be careful with this type of substrate. How many different types of beta hydrogen in that molecule? Do we see 3? I see 1 type down here. That's on the adjacent carbon. I see 1 type there. Do we see 3 types, or do we see 3 places that could be acidic, but how are they related? What's the relationship between that one and over here? They're the same, aren't they, because of symmetry. See what we did in chapter 5? All the symmetry, asymmetry. Now you can have a good sort of considered opinion about what an organic molecule looks like. This thing is symmetrical. So if you took off from the left side, you get the same product as you would from the right side. So there are only 2 different types. That's why I get 2 different products. So in terms of the actual mechanism, the base comes in, and it grabs one of those hydrogens, pushes the electrons into the carbon, and the bromine breaks off, all because you want the charge to go from O onto the Br. Santigantas both yawning at the same time. I haven't seen that one yet. That was pretty good. Huh? Very good. Hopefully you can both be awake on Friday at the same time. Well, that's your loss. It's okay. Right, my 2 products. Look at those 2 products. Think about now what we started with today. I have one alkene here, which is a certain shape, a certain pattern, and I have a different alkene over here, which is a different pattern again. Which one do you think is more stable, left or right? The one on the left. What's its classification? It is tetrasubstituted. What about the one on the right? Tri-substituted, right? So now we can talk about thermodynamics next week. We can talk about patterns in terms of which is more stable, which one do you get more of, and we deal next week with the reversibility. Let me ask you this question before I draw a reaction profile. Do you think this process going from O- to Br- is going to be reversible? No. Okay? To go backwards, this molecule methanol has to give up its proton. If you need to go backwards, that proton has to come off again. What's the pK of that proton? 16. How acidic is that? Not very. So there's not anything on the right-hand side that will allow for the reverse to happen. So people have asked me this question. What type of arrows to expect on this exam? Well, acid-base reactions, you can do both. You can do the equilibrium, you can do one side favored. This sort of stuff, it's all going to the product. Next week will change, but right now it's all going to the product. Anybody want to say anything? Taylor, you all right? Rayanne? You'd tell me if it wasn't, wouldn't you? You would. You're not shy. No, I didn't think so. Johnny N, how are we? Okay. So what we'll do now is get rid of that stuff, and I'm going to try and draw a reaction profile, because this has been something that people have been asking me this week about how do you predict these things. So let's go ahead and do that. Let's get rid of some of this noise. If it'll allow me. Come on. I need to get out of this pen thing. There we go. Let me get out of that. So, I want to try and draw a transition state, and I want to try and draw a mechanism that matches a reaction profile. So what I'll need to do here is set up some organic reaction. Let's set up cyclohexyl bromide. Reacting this with our friend Kotbu, as we call him. Kotbu, like a cartoon character, Mr. Kotbu. K-O-T-B-U. And Mr. Kotbu is rather large. Can't do SN2 reactions, poor fella. He can only do elimination reactions. And we're going to do this in some type of solvent to confuse you, but in reality that's what we use. And we're going to use DMSO, polar aprotic. Why not use a protic solvent with a base? It will get deprotonated. Yeah, it will get deprotonated. So polar aprotics are good for this. And what I'm going to make on the right-hand side is an alkene, and I'm going to get the conjugate acid of Kotbu, so Hotbu, okay, and I'm going to get potassium bromide. And that potassium bromide, we've often said, we don't really care about it because it gets washed down the sink, but that's the driving force of this thing. That's why this works. You want to put the charge on the Br- if you possibly can. And we've said that the mechanism involves the base coming after this molecule, and it can't attack in an SN2 because it's too big. So my negative charge, having identified it, is going to go after that proton, and I'm going to kick out, and I'm going to do that. How many steps are involved right there? 1, 12, 3, 1. One step. So how many hills do I expect in my reaction profile? Just the one. So I'm very carefully going to draw my axes. Which one is this? This is potential energy, right? And what's the axis at the bottom? Reaction coordinate, which is not time, it is the progress of the reaction, going from left to right from starting materials to products. That's all it is. So we'll be careful here. We'll put the starting material there, we'll put the products down there. We'll have to deal with this again next week, but this is what's happening. If I've got one barrier, it's really that. That looks an awful lot like a simple SN2. It's the same reaction profile. But obviously, because we have different things happening, we'll get a different transition state. So the transition state is at the top. And that transition state has to take into account everything that's happening in that process. Only one thing is really, only one step, only, some bonds are breaking, some bonds are forming. But this is a bit more complicated than where we've been. We've got one arrow showing a proton coming off, we've got this arrow showing the proton donating its electrons to somewhere else, and we've got that arrow breaking off. I don't think we've seen a mechanism yet in which we had 3 arrows in one step. Okay, this is a good place to stop for the exam, but we've got 3 arrows now. So what do I need to show? How many lines do you think? How many dashed lines do you think I have in a transition state? 3. So I'm going to try and draw this carefully. All my carbons stay where they were, no changes there. My hydrogen's coming off. Mr. Cockboo wants to become Hotboo. Okay, there's my negative charge. So I use the dashed line to show that bond forming. And the proton is coming off. So I need a dashed line to show that. But I'm forming a pi bond here between these 2 carbons. So I need to show that with a dashed line. The pi bond is forming. Any more? What do I need to do to finish this off? Dash line to the BR because that indeed is taking off as a leaving group. That's not bad. Yeah, close. What's missing from this? What do I need to do to tidy it up? Charges and my square brackets. Don't forget your square brackets or else the physical chemist will get annoyed. And we don't want that. Transition state. Now, where do I put charges and how do we deal with this? Well, think about the changes that are happening. The O over here is negative, it becomes neutral in the product. What do I need to put on O in my transition state? Delta negative. It's changing. Where else do I put a charge? BR, and what do I use? Delta negative because it's becoming negative. And so that's kind of the thing I want to develop on Friday. If you haven't seen it before, you should be able to do it. If you've been keeping up and you've been sensible about this, you should be able to handle the questions, even if you've never seen things before. Because that's what you need to do in science, in medicine, in pharmacy, whatever else you want to do, in engineering. You'll be asked to do things you haven't seen before based on what you know. So anybody want to ask any questions? That's it for the test, right? If you have a pencil, put a line underneath. That's it. No more. Go ahead. So the H doesn't need a... Whoa, what's happening there? The H doesn't need a delta positive because it has enough electrons all the time. It's only when things are losing electrons or picking up electrons that you need to put charges in. Yeah?